We have 3 more reactions in Unit 9, all considered reductions. In this case, a reduction, we're going to look at it as a reaction where we add hydrogens. We know that oxidation, you're adding more bonds to oxygen and less bonds to hydrogen. Well, in this type of reduction, we are going to think of it as adding more bonds to hydrogen. Or there's another way to think about this. We are reducing a triple bond down to a single bond, or reducing a triple bond down to a double bond. Okay, so there are 3 reactions. For my class, you're not responsible for any of the mechanisms. Okay, but the mechanisms are in your textbook. We've seen this before. Look at reaction 9G, catalytic hydrogenation. So we were able to hydrogenate or reduce an alkene into an alkane. We're doing the same thing here. We're going to make an alkane. The other 2 are converting the alkyne into an alkene, cis and trans, or I should really say cis or trans. Okay. Let us start real simply with a reaction that you should be familiar with from the alkene unit, and that is catalytic hydrogenation. I have this as reaction 9. Totally forgot. 9G. Very easy reaction. We are going to start out with an alkyne, terminal or internal, doesn't matter, and hydrogen gas is added, and then you've seen this before, either platinum, palladium, or nickel. Those are the 3 main metals you could use. I'm going to use platinum. The danger here is that you're going to convert everything into a carbon-carbon single bond, but just make sure you count the carbons correctly. I would put dots representing the carbons that are part of the triple bond, and I see that I have 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. That's your final product. You went from an alkyne to an alkane. There are other reagents you could do. You might see something like this. H2. This is called palladium when you have a slash carbon. This is called palladium on carbon. So it's palladium coating on or deposited on some carbon. This is also a very good catalyst, right, to add hydrogen. And we are adding 2 equivalents, 2 moles of hydrogen for every mole of alkyne, because we added 4 hydrogens. At the end, we added 2 hydrogens, and here we added 2 hydrogens. Okay. That's it. What's interesting here is that you're reducing the triple bond down to a single bond, but it looks like we bypassed the alkene. It would be great if we could have that much control over a reaction where we could say stop. Don't go all the way to the alkane, stop at the alkene. And years later, after this reaction was developed, it did. Chemists did develop a way to get to the alkene. The thing is, you know that alkenes, if there are multiple groups on the double bond, you could have possibly cis and trans isomers. Okay. And chemists developed ways to differentiate or how to target a cis or trans alkene. But let's take a look first at this other type of hydrogenation. This is going to be using Lindlar's Catalyst, so we could say, so adding hydrogen gas with Lindlar's Catalyst. Catalyst. Same alkyne. We'll start with the same alkyne. Have H2 again. Here you're allowed to just write the word Lindlar's Catalyst. And what we do is we change the triple bond into a double bond. So we still have 5 carbons. You know that double bonds are trigonal planar, so we'll draw a zigzag as well. So we get the alkene. Alkyne to the alkene. I'm actually trying to fit all 3 reductions on the same page, so I'm going to try to cram some more information here without taking up too much of the page. Lindlar's Catalyst. Okay, Lindlar's Catalyst is actually this. It's palladium with, calcium carbonate. CaCO. Sometimes they call this poisoned palladium. Isn't that a cool name? Poison palladium? Because the palladium up here, this is platinum actually, but if you use palladium, just plain palladium metal, okay, you will go all the way down to the alkane. But if you sicken it, if you make it a little less reactive, then you'll stop at the alkene by using what's called poison palladium. But the inventor, Lindlar, people just use his name, Lindlar's Catalyst. Okay. What's interesting about Lindlar's Catalyst, though, is that we know there could be cis and trans alkenes possible. For this case, no, there is no cis and trans for this alkene because this carbon has 2 hydrogens, 2 of the same things. Okay, so you can't have same side, opposite side. But what if we had this alkyne? Let's make it 5 carbons still. But now we'll put the alkyne in the middle. Okay, H2, Lindlar's. Okay. Put your dots. Okay, because we're still going to have 5 carbons and we're still going to have an alkene now in between these 2 dots. If we're counting from the right, carbon 2 and 3. If you think about maybe not the mechanism, but just physically where the atoms are, do you remember what happened when we did just a regular hydrogenation with metal? The hydrogen laid on top of the metal and presented its 2 hydrogens upwards. Okay, well, upwards. And what's happening is that, well, I'll just draw it. I think I've drawn this before, but if we have, let's use palladium again, and the H just sits on the palladium. And eventually, the H's bond to the palladium. But as that alkene is floating, wherever that first hydrogen adds, the second one has to add on the same side because they are, well, they're adding on the same face of the alkene. That's why we got, we said this was syn addition. Remember syn addition? Okay. Well, if we're doing syn addition still with Lindlar's Catalyst, then the 2 hydrogens that we're adding will add from the same side. And we'll definitely see this if your alkyne has a group on each side. Let me show you what I'm talking about. The trick is to draw the double bond. We know we're going to go from a triple bond to a double bond. Draw the double bond horizontally. What is on the left? We have 2 more carbons. 1, 2. What is on the right? We have a methyl group. This happens to be cis because the 2 H's added on the same side. Okay. You don't have to draw the hydrogens, obviously, but now we get a cis alkene. It's just easier. I know we learned E and Z, but it's just easier to do cis and trans because with these alkenes that we're making, we're always adding 2 hydrogens. So it's very easy, right, to see that 2 groups are on the same side or not. Okay, same side or opposite side. In this case, the same side, cis same side. Okay. But in terms of E and Z, this is definitely also E. No. Z, the same side. You don't need to know the mechanism, and I don't think I've ever taught you the mechanism. I did show you a little picture, right? Also in the alkene unit, where the hydrogen lays on top of the metal, and when one hydrogen adds, the other one adds at the same time on the same side. 9I. Last reaction that I will go over for Unit 9, alkynes, at least for now. But now we have to get the trans alkene. So this comes a little bit later, and this is called dissolving metal reduction. Let me draw you an example. And now I'm going to use an alkyne that has groups on both sides of the triple bond, because now we're going to have to aim for the trans alkene. The reagents are this: Na. Sometimes we put the word metal, but this is not the ion. This is not Na+. Sometimes they'll put 0 as Na neutral or sodium 0. That's a metal. That's not an ion. That's a big difference because ions will dissolve in water. Metals typically don't. Yeah, I'm going to stay with that. Metals typically don't. Okay. I'll just put 0. And it dissolves. Well, I said metals don't dissolve in water, but it does dissolve in liquid ammonia. We're going to make the transalkene. If I told you, convert this alkyne into the transalkene, would you know how to draw it? Draw the double bond horizontally, and just ask yourself what's on each side. We have 2 carbons on the left, and we have a methyl group, 1 carbon on the right. And now you don't have to draw your hydrogens, and actually I'm not. But do you see how this is now a transalkene? Transalkene. Okay. What else? Don't get this confused with NaNH2. Right? This is not an acid-base reaction. So these reagents are not NaNH2. And maybe I'll have time to go over some examples, okay, to kind of get you trained into drawing these products for these reactions. We're up to 9. A, B, C, D, E, F, G, H, I. There's 9 reactions. Although some of them are very similar to each other, like the reductions, and a lot of them are analogous to something that you do know, hopefully well, the alkene unit. Okay. The other thing I want to say is others or other reagents. They may look like this. Like I said, literally they'll write out the word metal, and a metal, but always should have liquid ammonia available. Okay, so Na0, Na metal, okay, or just plain Na. Okay, you shouldn't assume that that's Na plus because it's not Na plus. It's not the ion. Okay. The mechanisms are in the textbook. This mechanism actually is really interesting. It's a combination of a radical mechanism and also proton transfers. Okay, but again, let's not worry about that. It does end up making, right, the more stable alkene because trans typically is more stable than cis. Okay. that's it for the list of reactions, A through 9. At least for the fundamental reactions of alkynes. And for my class, I think that's where we'll end. But, you know, this chapter, or sorry, this unit, sure, there's 9 reactions, but the goal of this unit is to teach you how to start putting together synthesis. Okay, so there will be some more videos where I'll go over examples of how to apply these reactions and other reactions that we've learned in the past into syntheses. But for here, let me just go over a couple more fill in the products. Right? For instance, if I have this, I'm going to change it up a little bit. Okay, I'm going to put the triple bond down like that. Could you draw the products for, well, I'm going to start out kind of tricky. NaNH2 versus NaNH3 liquid versus H2 Lindlar's cat. Okay. What else can I do? In the video preceding this one, I think we did hydrations. Okay, it's getting a little bit cramped here. But one hydration was H2O, H2SO4, HgSO4, mercury 2 sulfate. And yeah, I didn't plan this out very well. I wasn't planning to do a roadmap right away. Okay, I'll do it up here. The other hydration, non-Markovnikov, SiA2BH. We could also use BH3. It's just that it's not going to be as selective for the non-Markovnikov pathway, but it will still be the major product, the same major product as if I had used the SiA2BH. Right, this is hydroboration oxidation. Oops, NiOH. Yikes. Again, typically a professor's task is to present the material, maybe go over some strategies on how to study that material, maybe encourage you to do practice problems either with your partner or during office hours. But it's really the student's responsibility to find the best way to study the material, whether it be roadmaps, whether it be note cards, whether it be one-page study sheets. The reorganization of your thoughts and of these reactions is really the responsibility of the student. Okay, so one way that I like to study these reactions is a roadmap, and this is just fill in the product. Eventually, I would like to be able to see the product and then fill in the reactant, so cover up all these arrows, all the reagents and the arrows, and that will definitely help with synthesis. Okay, so again, the main goal for this unit is to practice synthesis, but we gotta master the individual reactions first, or else synthesis is going to will seem like an impossibility. Pause the video, draw these products, and come back when you're done. I would estimate 1, 2, 3, 4, 5. If you're very good and you've studied, 5 minutes. If not, that's perfectly okay. Use your notes. Use your textbook. Okay, you are expected to use your notes and textbook at first. All right, and with those resources, you really should strive for perfection. Okay. And then later on you'll try it without those resources. Alright, so go ahead and pause the video and come back when you have at least something for each arrow. Okay. I'm going to do the hydrations first, alright? And I know I drew the triple bond kind of weird. It's pointing downward, like this, sort of like a substituent. But we know when we name it, right? We name it by numbering this as carbon number 1. The end closest the triple bond. Forget about that. But I think it's important to put the 2 dots. If this is not apparent, you gotta look back at your notes, because your notes do explain what to do here. I'm adding something to each carbon. In a Markovnikov fashion, I'm adding water. My double bond oxygen will be on this carbon. Look at where my 2 dots are. So we do have 2 carbons hanging off of this butane chain. Those are your 2 carbons, and I put the oxygen there. It goes through an enol, but I'm not asking you for the intermediate. I'm just asking you for the product. If you are having trouble doing this with your notes, then you'll need to, I suggest that you talk to your professor or your student teaching assistant. What's the opposite of this? It's this hydroboration oxidation. So if I do the same carbon skeleton like that, okay, let me zoom out a little bit. You see how those are the 2 same carbon skeletons? But now the double bond oxygen is at the end. Okay. And for aldehydes, I typically draw the hydrogen, but you don't have to. Alright? There's your aldehyde and ketone. For the alkyne, that's terminal. I wanted to use a terminal alkyne because what is this? This is a strong base. Do you realize that this is Na plus, NH2 minus? All we're going to do is deprotonate the terminal carbon. Okay, again, it looks a little strange because I drew it vertically, the triple bond, but we're just stripping off this proton right here. I wanted to do this reaction. Okay. You could definitely go through your notes and ask yourself, was this reaction 9A, 9B, 9C? I believe that's going to help you reorganize your thoughts, even though your professor is never going to ask you, is this reaction 9D or 9E or 9F? The thing is, you could put it down here, right? You could put what reaction it is so you could refer easily to your notes. Okay? You want to be able to use your notes. You don't want to be searching for pieces of information that you know you've seen, but you can't find. Right? So I'll take a guess. A, B, C, D, E, F, E, F. So this is reaction 9E, right? And this was reaction 9F. Okay, so that way when you come back and study, you can say, oh, I have no idea what was going on here. Let me look through my notes for reaction 9F and see how to do this reaction. Okay. Now look at these 2. I warned you in this video not to confuse sodium amide, NaNH2, with sodium metal with liquid ammonia. They look very similar, but this is converting it into an alkene, into a transalkene. But what do you notice about this triple bond? The triple bond here doesn't have a group at the end, so there will be no cis or trans. It's just a plain alkene, no cis and trans. And the double bond now, again, is between the 2 dots, just like the triple bond was between the 2 dots. This was reaction 9I. And this Lindlar's is reaction 9H. Okay. The thing is, since there's no cis and trans, your 2 alkenes, whether you do it with dissolving metal or Lindlar's catalyst, the 2 alkenes are identical because neither of them have cis and trans. If you really wanted to practice cis and trans, then what would you do with your alkyne? You would change it, right? You would change it to this, maybe. Change it to an alkyne that has a group on both sides of the triple bond. And again, I'm doing this purposely vertical so you don't freak out when you see it on an exam. Most of the time your triple bonds will be drawn horizontally or slanted horizontally. Right. Given this one here. Alright. So here, what you want to try? You want to go ahead and do your same reactions. Or how about this? See, this takes practice. I want to draw the cis and trans version of this molecule. So the trans version would be looking like that. Zigzag. The cis version would look like this. Okay. Practice your bond angles. You know that double bonds, that carbon geometry is trigonal planar. Okay. Cis, trans. Now it's your responsibility to know your reagents so well that on an exam, without any notes, could you fill in the arrows? What were some other reactions since we're on this sort of roadmap review? Let me give you this. Terminal alkyne. And now I am going to give you a list of reactions to do stepwise. Not stepwise, but to do in order. Oh my goodness. Okay. NaNH2. Question mark. Okay. Then I want you to take that molecule and I want you to maybe react it with this alkyl halide. And we'd have that. You'll have this molecule here. Then I want you to take that molecule and I want you to react it with Lindlar's Catalyst. No, not Lindlar's Catalyst. We haven't seen this one on this page yet. Just catalytic hydrogenation and get a third product. See, this is synthesis. Not the synthesis that I typically ask. This is an easier synthesis where you're given the reagents and you fill in the products. But a true synthesis is everything is covered and I give you the final product. Okay. Yes, the final product. I'm trying to think of another reaction that I could do. Okay, I'm probably going to get in trouble for this because I'm doing this off the top of my head. But you'll fill in the product here, and then I'm not going to draw you the product. I'm going to ask you to react it with a reaction that we learned in the previous unit. Br2. Remember what that is? Okay. And I think we should get one major product here. Let me just double check. Yes. Okay. Alright. If you want, I'll do this with you. Pause the video, fill in the question marks, and then come back. Okay. I'm going to have to go through this a little bit fast, so I want to try to be under half an hour. Deprotonation. This is alkylation, or you can think of it as substitution. So I'm connecting to this dot. So there's my dot. The dot has a bond and then this triangle. Okay. Lindlar's Catalyst. It's a little cramped. Draw the double bond first. What's on the right is a dot and a triangle. What's on the left is 1, 2, 3. 1, 2, 3. Cis. And then, no. This is full hydrogenation. My goodness. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and then a triangle. My bad. 1, 2, 3, 4, 5, 6, carbon of the triangle. 1, 2, 3, 4, 5, 6, carbon of the triangle. And then radical halogenation, the radical unit. 1, 2, 3, 4, 5, 6, then the triangle. The most substituted carbon where we could find a radical or make a radical is right here. That's where we put the Br. The thing with a synthesis, an actual synthesis, is if I cover up everything, oh boy, how do you do that? Would you be able to string together a bunch of reactions to do this problem? Question mark? List of reactions to get to this. Okay. That's a good synthesis actually, because it incorporates a lot of unit 9 reactions and one radical reaction. I forgot what unit that was. I think that was unit, well, I'm not going to guess. Okay. That's it for the list of reactions for alkynes. Possibly I'll post some review videos and problem set videos after this one, but you have all the information now to be successful with the Unit 9 problems.